All right, good evening, everybody. Just wanted to go through paper one on a page to let you know what my thinking was for each of the statements. It's going to be quite quick, so you can pause this at any time and replay if you've got any questions, email. So, simple definitions. Vectors have a number with a unit and a direction. We also can say that they have magnitude. If magnitude is too big of a word for you, just something that you can put numbers on that leads to some kind of a scale, bigger to smaller. You can also go into the minuses. Examples are displacement. So here is point A, here is point B. Straight line between those 2 points is my displacement. Velocity will be measured in meters per second, and it will also have a direction. Forces, anything measured in newtons. Acceleration, remember the units for that are meters per second squared. And momentum. Momentum is mass times velocity, and it's the idea of how difficult it is to make something change its velocity or its direction. More momentum is harder to stop. Scalars will only have a number with a unit, so there'll be no direction associated with your scalar measurements. Distances, so if I started at A and I walked around and around and around and around and I round up at B, this would be called my distance. The symbol for displacement is x. Speed also measured in meters per second, but without a specific direction. Mass measured in kilograms, you can either have inertial mass, which is how hard it is for a force to change the motion of an object. So if you apply a force to an object, how difficult it is to move it, we call that inertia. And it is also measured in kilograms. Temperature, degrees Celsius. While we say that temperature goes up and down, that doesn't mean that it has a direction. We're just talking about the number increasing and decreasing. You can't have 5 degrees Celsius left. And energy is the ability to do work. It's measured in joules. The acceleration due to gravity, that should be newtons per kilogram actually. Acceleration due to gravity is 10 meters per second squared. And the gravitational field strength of the Earth is 10 newtons per kilogram. So whenever you get G in a question, that will always equal 10 unless you were told otherwise. Not 16, 10. Okay, distance time graphs. The slope on the line shows the speed. If you have a steeper line, then it is a faster speed, so this will be faster. No slope here means no motion. So let's say this is, 1, 2, 3, 4, 5, 6 units of distance, probably 6 meters. This object has been at 6 meters for 1, 2, 3 seconds. So therefore, it is a stationary object. Velocity time graphs show you more information. Slope on the line shows acceleration. So if I take the end velocity and the start velocity, this is going to be v, this is going to be u, and I divide that by the time taken, I will get a is equal to v minus u divided by t, or the acceleration of an object. Steeper lines show greater acceleration because they have had a greater change in velocity in the same amount of time. No slope means no acceleration. This is different to my distance time graph because my object is right now moving at 6 meters per second. It is not stationary, it is just traveling at a steady speed. And the area under the line is equal to the distance that the object travels. So if I wanted to find out the distance that my object traveled, traveling 6 meters for 3 seconds is the area under the line. I multiply my 3 by my 6, giving me 18 meters traveled in the time that we're talking about. Sorry for my handwriting again, I'm using my mouse. Negative velocity and positive velocity are at the same rate, but in opposite directions. This is especially important if you're looking at momentum calculations. They are higher tier only, those, so don't worry about it. The momentum before a collision is equal to the momentum after a collision. If I have got 2 objects, object A and object B, traveling towards each other, this is 2 kilograms, this is 2 kilograms, this is 2 meters per second, and I want to figure out what the meters per second of this thing is. And if I'm told that the total momentum is 20 kilogram meters per second, then I can find that out. But let's just say that they've done this collision, and I want to know the velocity that B is going after the collision has taken place. The momentum will still be 20 kilogram meters per second, and the mass will stay the same as well. So if I now know that A is traveling at minus 1 meter per second, I can figure out what velocity B is going because the momentum will be the same. If you would like to, have a look at YouTube. There is a video on momentum there for some more details. At a constant speed, acceleration at a constant speed if you're changing direction all the time. If we imagine a circle, if there is an object that is moving in a circle, even though it's traveling at 2 meters per second, if it is constantly changing its direction, then we say that it is accelerating. And it's accelerating because acceleration is a vector quantity. It is a speed and a direction, a size and a direction, a magnitude and a direction. Newton's first law, forces affect motion. The resultant force is what will determine what a object does. If there is a resultant force in a particular direction with a particular magnitude, then that is what will describe the object. The resultant force is the sum of all the forces acting on an object. And remember that I can have positive newtons, plus 2 newtons, and negative newtons. That does not mean that these negative newtons are smaller. They are not. They're just going in a different direction. Newton's second law, F equals A times m. Acceleration is proportional to force of the object, force applied on the object, or the mass of the object. This just means if you increase force by 1 unit, you will get a 1 unit increase of acceleration. Newton's third law, equal and opposite. For every action, there is an equal and opposite reaction. Forces from two objects interacting will always be equal in magnitude, but opposite in direction. So if I have got something orbiting around planet Earth, let's say it's the moon, the force due to gravity from the Earth on the moon will be equal to the force due to gravity from the moon on the Earth. They are called action-reaction pairs, and they exist whenever forces interact. Okay, energy transferred is also known as work done. Delta means the change, so delta M will be the change in mass, delta H change in height, delta EP will be the change in potential energy. Energy is the ability to do work, and the unit is joules. Gravitational potential energy is found in objects that are above the Earth. And we can talk about the change in objects' height. So if I've got a 1 meter high table and I move my object up here to 2 meters, then the amount of gravitational potential energy that it has gained is not 2 meters. The amount of gravitational potential energy it has gained is the difference in height. So therefore, delta H will be 1 meter. Gravity will be 10 newtons per kilogram. The mass will be, let's say here it's 2, and I can find out my GPE, or my change in GPE, by multiplying 1 by 10 by 2, 20 joules. EK, thermal kinetic energy, is energy found in objects that are moving. Thermal energy, let me just see if I've said this. Okay, I might say this later on, but I'm going to say it now. If I have an object A with a certain amount of gravitational potential energy and it falls towards the Earth, when my object A is just about to hit the ground, then all of that gravitational potential energy will have been transferred into 100 joules of kinetic energy, assuming 100% efficiency. Again, if you go to YouTube, there's a video describing this in more detail. Thermal is internal energy, so thermal energy increases is going to cause an increase in the internal energy of the object, increasing the kinetic energy of the object inside the atoms that actually make up the object, and that will increase the temperature. And chemical energy will be found in anything that can burn or anything that can charge. Oh, and here we go. Falling objects, all gravitational before will equal all kinetic energy just before the impact. Forces are transfers. They actually do things. The transfers that we know, not just forces, are heating, making an object increase in temperature. Heat transfers go from hot to cold. Forces, including weight and gravity, all make stuff happen. Energy is the ability to do stuff. Forces actually do that stuff. Radiation will do things as well. Radiation will go from a source to an observer and cause an effect on that source. And electrical work, we'll look at that in paper 2. It's not very important for right now, but it is the energy that is transferred through coulombs. Friction is two surfaces moving over each other. Heat is lost in mechanical systems because of friction. This is usually as waste. Sometimes, though, friction can be useful, like when we're looking at the brakes of a bike. Lubrication reduces the effect of friction. Insulation reduces heating of surroundings by an object, or can reduce the heating of the object by surroundings. So if I have an object here that is cold and I insulate it, it will stop the heat transfer, increasing the thermal energy of the object that is inside my insulated box, or whatever it is. The conductivity is how easy it is to let heating occur. More conductivity is bad in this situation here. We do not want, when we want things to be insulating, we don't want thermal conductivity. Efficiency is a measure of how much energy is used usefully. Efficiency is useful energy divided by total energy. It's a number between 0 to 1, or you can do it in percentages. Nothing is 100% efficient, but we do sometimes assume 100% efficiency for the example of which would be the one above. Waves. Transverse waves oscillate perpendicular to the direction of the wave. Examples, what that means is that if I have got a wave traveling in this direction and I have got my particles oscillating up and down, then they are oscillating or vibrating perpendicular to the direction the wave is traveling. Examples are light, or in fact all EM waves, radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays, and water ripples. Longitudinal waves oscillate parallel to the direction of the wave. And all that means is as your wave is moving forwards and backwards, as your wave is going from left to right, in this particular example down here, then the oscillation of the particles is going forwards and backwards. Examples are sound and some seismic waves, push waves, P waves in particular. Shout out to Dizzle Howard for that. Frequency is the number of waves per second. Wavelength is the length of one wave in a transverse wave. Now, one thing I will say is that this kind of diagram isn't just for transverse waves. This kind of diagram can also be used for longitudinal waves, because the peaks here match the compressions of a longitudinal wave. Longitudinal waves are broken into compressions and rarefactions. Compression is where my particles are close together, like right there. So I'll label that as C and label that as C. And then the rarefaction is the part in the middle where the particles are spread out. Period is time for one full wave, is the time required for one full wave to complete its cycle. So let's say I've got a frequency of 1 hertz. That means I've got one wave every second. That means that after 1 second, I will have one wave. To find the period, it is 1 over frequency, or 1 over 1. If I've got a frequency of 10 hertz, that means I've got 10 waves per second. So that means in 1 second, how many waves would I have? Well, the period is, how long does it take for one wave to complete its cycle? I mean, pardon me. The number of waves per second is 10 hertz. 1 over frequency, 1 over 10, 0.1 seconds. So 10 waves a second, each wave takes 0.1 seconds to do that. Amplitude is the displacement of the particle or the relative amount of wave energy. Amplitude is measured as from the, we'll talk about particles just because it's the easiest way to describe it. Again, there's a video on YouTube if you would like to look at it for more detail. It is the total displacement from the starting position that a particle moves. So if I've got a particle here and it moves 1 centimeter in this direction, and then it goes, so 1 centimeter in this direction, goes back to where it started, and then goes another 1 centimeter in the other direction. Even though it is wiggled for 2 centimeters, that is not the amplitude. The amplitude is the maximum distance away from its starting position that a particle moves. Generally, higher amplitude in sounds means a louder noise. When a wave meets a boundary, there are 4 things it can do. It can refract, which means it slows or speeds up and bends. Towards the end means it has slowed down. Reflection bounces at the same speed and angle. This is what a reflection is. My wave goes in, hits my medium, bounces off. The angle between here and here will be the same. So I'll call this theta, and I'll call this theta 1. Okay, this can be theta 2, pardon me, theta 2, theta 1. Theta 2 and theta 1 will be the exact same angle in reflection. Absorption, down here number 3, it does not pass through the medium. The wavelength of this material is, the wavelength of this wave is interacting with this material and it was not able to get through. Transmission is where it goes through the medium, and this is here in number 4. Now, here we can see that my wave should just carry on to number 4. If there was no slowing down, then my wave just carries on, and it would just be this nice straight line. But we can see that this wave has refracted. It has gone from the position 4 to the position 1. It is bending towards the normal. If it slows down, that means it's going towards the normal. That's a memory trick just because it's both got OW in it. The normal line is the line that the light would normally take if there was no refraction or bending of any description. And if you ever want to measure an angle, you measure from the ray to the normal. So if I wanted to measure the angle of refraction here, angle of refraction, it would be between the ray and the normal. Normal line is the path light takes if there's no refraction. When light goes from less dense to more dense, it slows down and the wavelength decreases. Whenever you see this in these videos or in the sheet, it means decreases. Change of wavelength means different degrees of refraction. If you have got a lower wavelength, then there is going to be a lot more refraction. So blue light, for example, has got a lower wavelength than red light. Blue light refracts more. I know I'm talking very quickly, but there are videos that go into all this in more detail. This is just a snapshot. The velocity of an electromagnetic wave is 300 million meters per second in a vacuum. They will change their velocity when they go into a new medium. So when they come from the vacuum of space into the atmosphere of the Earth, they will slow down slightly. All electromagnetic waves are transverse and transfer energy. Radio waves, microwave, infrared radiation, visible light making up Roy, G, BIV, ultraviolet X-rays, and this is your symbol for gamma. Red light travels faster through denser media as it has got a longer wavelength. Just please remember that radio waves have got the longest wavelength, and then you should be able to logically figure out the rest. If radio waves have got the longest wavelength, then gamma rays have got the shortest wavelength. If they have the shortest wavelength, then they've got the highest frequency. If these have got the longest wavelength, then they will generally have the lowest frequency. Roy G. Biv is the order of light from high lambda, high wavelength, to low lambda, low wavelength. Gamma causes more tissue damage as it has got a higher frequency. If it hurts more, it hurts more. So this means that there is more energy transferred with a higher frequency. This means there can be mutations in your DNA which can lead to cancer. Microwaves can heat cells because the particular wavelength of a microwave is the right wavelength to cause the oscillation of water molecules, making those water molecules get more kinetic energy, increasing their temperature and therefore cooking our food. Infrared can cause skin burns because it's very good at transmitting heat. And making heat be absorbed by your body, radiating heat. Ultraviolet light, can damage cells, specifically cells in the back of your eyes or any kind of nerve cells, and can cause mutations to your skin, causing skin cancer. X-rays and gamma rays cause mutations because they hurt more, so therefore they hurt more. Higher frequency, higher energy transfer. Uses of radio waves. They can be used for television signals, for radio signals as well. They're useful because back in the good old days when there were no satellites, if Jimmy over here wanted to talk to Timothy on the other side of the world, if Jimmy was standing here, he wouldn't be able to get a clear line of sight to the name of the person I said over here. I can't remember that. But what we can do is remember that the Earth has got an atmosphere. This is the best drawing I have ever drawn. The radio signal, even though it can't get a clean line of sight from this point of the world to this point of the world, it can fire a radio beam into the atmosphere of the Earth, and there will be refraction. So that refraction allows radio waves to be sent around to the other people on the other side of the world. Microwaves can be used for cooking, but they can also be used for communications. Microwaves, when they are sent up, have the right wavelength to penetrate the atmosphere and go to the satellites that are in orbit. Infrared can be used for cooking as well as microwaves. So you've just got to absolutely make sure that when you're looking at the multiple choice question, you check the wavelength. Microwaves have got a higher lambda, so they're going to have more nanometers. Infrared that's used for cooking will have less nanometers. They're also used for taking thermal images at night and optical fibers for high-speed internet. Visible light is used for vision and photography. Ultraviolet is used for security marks. So when someone puts a bill underneath that purple light, checking for the security ink, then that's what they're looking for. They can also make fluorescent lights, and they're good for disinfection. So if you've used quite a lot in fish tanks, if you've got a tank, then you generally set up a pump, and that pump goes through an ultraviolet light, and the water that comes back in has got no microbes because ultraviolet is a high-frequency electromagnetic wave that is able to destroy the cells of any bacteria. X-rays are used for internal scans, medical scans, and gamma rays are used for sterilization. Now, if I pointed gamma rays at a piece of food, I would completely destroy all the biotic life on that piece of food, and I wouldn't actually cause any damage to you because I'm just killing the stuff that's on the piece of food, and the piece of food is already dead. Well, you'd like to think so, anyway. It can also be used for cancer treatment. So people ask, why is it that I will use gamma rays to treat cancer if it is cancer causing ionizing scary bit itself? So let's say that this is a person who has got cancer and the cancer is here in this location. If I send one gamma ray through that location, then that's bad, but it's not as bad as cancer. Because gamma rays are only weakly ionizing, we'll come on to this in just a second. So what they do is they surround you so that you get loads of gamma rays that are all intersecting across that one point, and therefore destroying all the cells in that area and hopefully destroying all the cancer cells as well. Oh, wow. Okay, so each of these gamma rays by themselves are not that scary, but if you've got lots of gamma rays focusing on one point, then that point will be destroyed. Now, how do we make radio waves? Electrons oscillate in wires. Oscillation is another word for vibration. So if you put a current, an alternating current, through a wire, then my electrons will oscillate and they will make radio waves. Because you're giving energy to electrons, this is causing, here's my nucleus, here's energy level 1, here's energy level 2. If I give it energy by putting it through an alternating current with a source of potential difference, my electrons will jump up to a higher energy level, and when they fall down, they will release electromagnetic waves as photons. EM waves are released when electrons fall from higher energy levels. Okay, if you don't know this by now, then please start panicking. Protons have got a mass of 1, a charge of +1, and are located in the nucleus, which is here. Neutrons have got a mass of 1, a charge of 0, they are neutral, and they are also found in the nucleus. So protons and neutrons are responsible for all of the mass, most of the mass. We can say that the mass of an electron is 0. It is actually 1 over 1,800 odds. It's a very tiny amount of mass compared to the protons. You would need to have an atom with 1,800 protons to have an electron cloud with as much mass as a single proton. Isotopes are the same number of protons but a different number of neutrons. This is carbon 612. This is called the proton number or the atomic number. That means it has got 6 protons. The mass number is the number of protons plus the number of neutrons. Now, if I've got 6 protons, the rest of the mass must come from the neutrons. 12 take away 6 is 6, and this is a neutral atom, so we'll say that it has got 6 electrons. This is an isotope because it has got the same number of protons but a different number of neutrons. We started with 12, now we have 13. The proton number is easy, it is 6 protons. If I wanted to find the mass number, well, the mass number is the massive number, and that is the number of protons plus neutrons. So that will equal 6 plus the number of neutrons. So whatever number, 13 take away 6, it'll be 7 neutrons. And because this is still a neutral atom, it will have 6 electrons. Here, this is still carbon 614 because the mass number is the massive number. It doesn't matter if the 14 is at the top or at the bottom. It is 6 protons. That's easy enough to do. The 14 mass number will equal the 6 protons plus the number of neutrons. Whatever number plus 6 equals 14 is the number of neutrons, so 8 neutrons. And it's a neutral atom, so there will be 6 electrons. Atoms form positive ions by losing electrons. If there is so much energy given to this electron that it leaves the orbits, then this will become an ion. An ion is a charged atom. Electrons increase energy levels with absorption of EM radiation, and electrons decrease energy levels with emission of EM radiation. Absorption means going in, emission means coming out. This is not nuclear radiation. Nuclear decay releases radiation. Unstable atoms decay randomly, but predictably, and release energy as radiation. If I flip a coin once, I've got a 50-50 chance that it's going to be heads or tails, but I can't predict which one it's going to be. However, I can predict that after 1,000 throws, that 500, roughly 500, very probably very close to 500, 500 will be heads, 500 will be tails. Releasing energy makes atoms more stable. This is why nuclear decay happens. Atoms want to be at their lowest energy level possible. So these unstable atoms, after they have decayed, will become more stable atoms. Background radiation is the constant low-level natural radiation that we have evolved to be able to cope with. The 2 most common causes of background radiation: radon gas from the ground and cosmic rays from the air, from the sun, from the sky, from space. Food and drink are also a source of background radiation: bananas, Brazil nuts. Medical scans, PET scans, medical scans, X-rays, and also medical treatments, gamma rays, and nuclear bombs. I put down nukes there so I could sound cool. These are all sources of background radiation. Activity is how we measure the amounts of activity is how we measure how radioactive a thing is. It is also known as the rate of decay, and the unit is the becquerel. More becquerels means more activity. The count rate is the number of decays per second. Okay, alpha radiation, the symbol is A, or 2,4 helium. Now, the reason for that is alpha radiation is made up of 2 protons. There's 1 proton here, and a second proton here, and 2 neutrons, 1 neutron there, and 1 neutron there, being emitted from the nucleus. Now, if I was to draw a helium atom, I would draw 2 protons, 2 neutrons, and then I would add 2 electrons in shells or energy levels around the atom. So this would be an atom of helium, and this is the nucleus of helium. So we can say that alpha radiation is the same as a helium nucleus, which is why we give it this symbol. Beta minus has got this symbol. That's the Greek letter beta, or electron with 0 and then -1 at the proton number level. Not the mass number level, the proton number level. It's emitted from the nucleus. The neutron turns into a proton and releases a high-powered electron. Fires out of the nucleus, not out of the shells. Positron radiation, beta positive, or you can have this symbol, or you can have the symbol of 0 + 1e, which is a symbol for a positron that is being emitted from the nucleus. When a proton turns into a neutron and a positron. Proton turns into a neutron and a positron. A positron is like an electron, but with the opposite charge. Gamma rays have got are electromagnetic radiation. They have no mass and no charge, so they are non-ionizing but very penetrating. Oh, that's upsetting. Look at that. That's going to upset me a lot. Child says to a teacher, PP. Teacher says to the child, no, P, that makes me sad, a negative emotion. P now says to teacher, that made the child happy, which is a positive emotion. So, what's all this for? Alpha radiation is made up of 2 protons and 2 neutrons. Beta, this is sad emotion. Negative is a neutron, which is what the N stands for, turning into a proton, plus a negative electron. Beta positive, P now, happy. Happiness is a positive emotion. The proton turns into a neutron and a positive electron, a positron. We can write these reactions using nuclear equations. So here's some carbon-14, an isotope of carbon, and it will turn into nitrogen when it undergoes beta-negative radiation, because one of the neutrons is turned into a proton, increasing the proton number. The mass number stays the same, though, because the mass of a neutron is equal to the mass of a proton. So let's see if these make sense. -1 + 7 = 6. Yes, it's true. 0 + 14 = 14. Yes, that's true as well. Types of radiation, how ionizing they are, penetrating they are, and what charge they have. Remember, ionization is what can cause cancer and damage to cells. So the higher the ionization, the higher the danger. Penetration is how the objects are able to transmit through materials. So alpha radiation can be stopped by air, paper, skin. Beta negative and beta positive radiation can be stopped by a thin sheet of aluminium. And gamma radiation needs thick lead or concrete, because it is the most penetrating. However, because of the charge that is on alpha radiation, 2+, it is the most ionizing, therefore the most dangerous if it is in contact with your skin cells, with your cells. Beta negative are both mediumly ionizing. They're half as ionizing as alpha radiation, so still quite dangerous. We don't really want to be messing around with those. And gamma radiation, even though it's not very ionizing, it's just slightly ionizing, but still something to be worried about. Especially because it's so penetrating. So long exposure for an unsealed gamma source can lead to cancer. Atoms before the 1900s, just simple spheres made of whatever it is. So you'd have a simple sphere of lead. An element of lead would be made of a simple sphere of lead that we just draw like that. And there we go, lead. However, in 1911, we discovered the electrons, and we put them as plums in a pudding. So we said that there was a cloud of positive charge with little electrons scattered about the place, like plums in a plum pudding, raisins in a scone, chocolate chips in a chocolate chip cookie. After 1911, Rutherford's famous alpha scattering experiment, where he put some gold foil, AU is a symbol for gold, and he fired alpha particles at that. What they realized was that the alpha particles were either bouncing off of a very positive and very dense bits of the nucleus, or they were being repelled away from it. This showed us that the nucleus was positive, that was very dense. Most of the mass was in one place because most of the alpha particles that were fired at by foil just went through the empty spaces between the nuclei. Then Bohr discovered electron levels. Half-life is the amount of time needed for 1/2 the nuclei in a sample to decay or for activity to half. Again, go onto YouTube and there is a lesson just on half-life up there for you. Radiation damage, it damages because it can ionize cells, it can damage cells, it can cause mutations of DNA, and it can lead to cancer. There are 2 ways that you can get radiation damage. One is through contamination. Contamination is when you are constantly in contact with the source, the object has now become radioactive. For example, if you ate a bit of polonium, you would have polonium inside you, you would be contaminated with that polonium, and you would become radioactive. Irradiation is when you're exposed to radiation, but you're not radioactive after. You're not exposed to the source, you are just exposed to either alpha, beta, beta plus gamma rays. You are not radioactive afterwards, and everyone can touch you and be absolutely fine and safe. You may not be healthy, but you run no risk to hurting anybody else. How do you protect yourself? Distance. Keep yourself away from sources by using tongs, keeping them at arm's length, and not pointing them towards you. They are directional. So if I have this is generally what they look like when you get them at school. You've got like a little metal pin, and then all the nasty radiation comes out of the metal bit. Don't point that at you, and you should be absolutely fine. Limit your dose. You can't play with radioactivity too much because overexposure or repeated exposure can lead to cancer. Don't forget protective clothing like lab coats. We do not accept goggles. Goggles do not do anything unless they are special goggles. If you would like mica screened goggles, or if you want to remember, I know you can't have lead line goggles because then you can't see them. I can't see through them. And just some kind of protective clothing. Lab coat is the best because it is good at stopping alpha radiation, which we're so worried about. And no licking. That's just a joke one. I was pretty tired by the time I finished making this, so I'm trying to be funny. Now, what's going on here? Okay, that's the content, all right? So basically, you're going to get questions and all that stuff. Here, though, we're going to have a little chat about how to answer some questions. Physics experiments are about measuring values of terms in equations. So I'm going to put down speed is equal to distance divided by time. This is a term, and this is a term, and this is a term. So how do we measure these terms? That's what most experiments are about. So if I wanted to find the speed of a year 7 running out of school on Friday after half term, I would measure the distance that I saw the child running for and the time. So I've measured this term and this term. If I divide the distance by the time, I will get the term that I'm looking for, the speed of the child. For experiments or any other question, really, always try to find an equation that fits the experiment or fits the question. How would you measure the velocity of a wave? Well, velocity equals frequency times wavelength. So you're going to have to measure the frequency and the wavelength to find the velocity. And when you get a question about any kind of practical, what the heck is going on here, Mr. Mouse? Thank you very much. If you get a question about anything to do with anything practical or anything measuring, I want you to remember EPIC RAVE. EPIC stands for what equipment do you need to measure the terms or the dependent variable, or indeed to measure and protect the independent variable. What equipment do you actually need? Is it a ruler? Is it a stopwatch? Is it a light gauge? Is it a microphone? What is it? Write it down, be specific about how you use the equipment. What is the procedure after you've got your equipment out? If you don't say how, if you just say get a ruler, get a stopwatch, divide the distance by time, you're not going to get a mark. Get a ruler to measure the distance, get a stopwatch to measure the time, divide the distance by the time, will get you the full marks every single time. How are you measuring the independent variable or the important value? So is it something to do with height? So is it perhaps that we've got a child on a swing and we want to figure out there's position A, there's position B. We want to figure out if they swing higher, if you push them more. What's the important value that we're looking at here? Well, we're looking for the height here, aren't we? That's what we want to measure. We also want to measure the force with which we are pushing the child in the swing. How are you measuring these important values? The independent variable for this experiment will be changing the amount of force. I'll push with 1 Newton, then 2 Newtons, then 3 Newtons, and see which one gets the greatest height. The control variable is how to keep all the other variables the same. So, for example, I might have a Newton meter that I use to figure out how much force I am pushing the child with. I will use the same person on that Newton meter. I'll use the same child. I'll use the same swing. I won't lubricate the swing between 1 and 2 Newtons. I will keep everything else the same apart from the force of the child being applied to the child and how high the child goes. How do I take an accurate measurement? How is it that I can make sure that my child, that I get the height the right way every single time? Take a camera, take a video, take a picture, and have a meter ruler beside that child so you'll be able to get a scale, something, anything at all to keep things the same. And then RAVE, repeat and find the average. Doing a repeat is not useful unless you average it. It's why we do repeats, to find the average. You can also repeat the experiment and change it slightly. So we found that the child was swinging their legs, which affected my experiment. So we tied their legs together because, you know, if you swing your legs when you're going on a swing, you're going to go a lot higher because of momentum. Actually, there's more physics. I can do that as a lesson. Repeat the experiment and change it slightly to see if it is going to be better, but then repeat it and find an average. Control variables must be limited so that any change is due to the independent variable changing. And that is it. The independent variable is the one that you were manipulating in order to see the effect on the dependent variable, the thing that you were measuring. We can reduce reaction times using automatic timers. Don't just say electronic, because human reaction time gets in the way of electronic timers too. Electronic timers are like stopwatches. They're not useful. Sound moves at 330 meters per second, so use big distances or microphones in a PC. What does this mean? If I'm finding the speed of sound between point A and point B, and I'm 20 meters apart, well, speed travels at 330 meters per second. So in like 1/100 of a second, the sound is going to pass me. It's going to be gone by after a second. Human reaction time is anything between 0.4 and 0.7 seconds. So unless you have got a big distance, then human reaction time is too slow to measure the speed of a sound wave. And you could also use a microphone or a PC. So if I want to find the speed of sound, I would have at A, I would have the sound being projected, and then I would have microphone 1 and microphone 2 connected to a laptop or a data logger. Microphone would give me time 1, microphone 2 would give me time 2. The difference in that time would be the time taken to travel this distance. I could measure that as 10 centimeters, let's say it's 1 second. I would then have speed is equal to distance divided by time. Speed is equal to 10 divided by 1 centimeters per second. Use markers when resetting experiments. So if I have a trolley on a slope and I want to see how mass affects the movement of the trolley, I could put a marker on my slope to make sure that my trolley is released from the same point every time. Light gates are only useful for trolleys and small objects. They're not useful for figuring out the speed of like a person running or a cheetah sprinting or a bird diving or whatever. They're only useful for small objects because they're literally about 15 centimeters across. Measuring radioactivity or anything really, sound amplitude, light amplitude, the effect due to gravity, anything at all. You keep your detector the same distance for the same amount of time. Repeats are only useful if averaged, and you reduce friction with lubrication, and insulation reduces heating transfers that you don't want. Here are two examples of using EPIC RAVE. So finding the speed of waves in a water tank, the equation you're going to use is v is equal to x divided by t. X, remember, is displacement, and it is measured in meters. The ripple tank is going to produce some waves. So a ripple tank is literally just a tank with ripples, and you'll see these waves moving from left to right. Get a ruler and put it down beside your tank. Get a stopwatch ready to go and measure how long it takes this wave to travel the 10 centimeters, 20 centimeters, whatever it is you've chosen. You then repeat and find an average, right? Because it's important to do that. That's the RAVE bit there. But before we get to that, we're going to talk about the important value. We're trying to find V. So we have to be specific that we are going to do V is equal to x divided by t. We've got the distance that the object travels, 20 centimeters. We've got the time taken to do it. Let's say it's 2 seconds. The velocity then is going to be 10 centimeters per second. Controls, keep the tanks at eye level. Don't stand here and watch this wave, because if you're looking at this and if you're looking down the tank at a side angle, then you aren't going to get specific. You're not going to get the numbers that it's passing. It's not going to be accurate enough. Use markers so it's easy to see 0 and 20 centimeters. 0 and 20 centimeters. It's difficult to see the little lines on the ruler, so let's make a big marker, like a big piece of paper or a piece of blue tack or something, so it's easy to see when the wave moves past. And repeat 10 times and find an average. 10 is good, 20 is better. If the waves are moving too fast, use a camera to measure the exact time needed for the wave to move from there to there. So if I take a camera and I'm looking at the video later on, you can see down there that there's the bar. If I see the wave move, oh, here's my wave. If I see underneath that my wave started moving at 2.1 seconds, and then I can see the amount of time needed before the wave passes to there, and it's 2.6 seconds, then 0.4 seconds on my camera will be the time needed for the wave to pass by the time the wave is going. Find the speed of waves in a metal bar. Well, this is something you do have to know about. First thing, you got to make a standing wave. So if I have got a bar and I hit it with a hammer, then a wave will move down my bar and back up again. We call that a standing wave. So the wavelength of the bar is the length of the bar multiplied by 2. So if this is 6 meters long bar, the wavelength will be, okay, stop being it now. Wavelength will be 12 meters long. I can't measure the speed in a metal bar because it's traveling like 1400 meters a second. Waves travel faster in solids and liquids than they do in gases. So the equation I'm going to be using to find the speed is the velocity equation, frequency times wavelength. So I got to find the frequency, I got to find the wavelength. What do I need? Metal bar, rubber band, 2 clamps, hammer, and a frequency add. Measure the length of the bar and multiply by 2 to measure the standing wave length. That gives me lambda. Place frequency measuring at next to the bar and hit with a hammer. That gives me frequency. The important value is V, so V equals F times lambda. That gets me my answer. The controls could be, if you're testing different metals, use the same length of bar, so it's the same wavelength. It really shouldn't matter because it will still have the frequency will depend on the length, but it doesn't really matter. Use the same rubber bands, or at least have them up on rubber bands. But the best repeat for this experiment is to repeat 10 times and find an average. I'm so sorry for my mouse going all over the shop. I don't know why it's doing that. It's my graphics tablet. Okay, this is the math section. There is a math practice section on www.whascience.com. If you go into the maths practice section, I have gone through all the mathematics in the maths practice session and made videos for higher and foundation. If you would like some more practice, please do so. You will have to know prefixes. So I'm going to give gigajoule here, and gigajoule is equal to 1 times 10 to the power of 9 joules. That is what this table means here. The prefix giga, symbol G, means that you multiply the unit by the number by 10 to the power of 9. So 6 gigajoules will equal 6 times 10 to the power of 9 joules. I'm not writing that down. Pico, I'm going to do micro then. Micro is multiply times 10 to the minus 6. So if I have got 6 joules and I want to figure out how many microjoules that is, they are 6 times 10 to the minus 6. 6 millionths of a joule. Triangles formula is not proof that you know the formula. So if we've got speed is equal to distance divided by time, and someone's asking you for time, and you do your equation, dst, this is not worthy of a mark. You must write down your equation. So first off, write down your speed equals distance divided by time, then do your triangle, and then you can write down your rearranged equation. Remember, a quick trick, if you ever want to find the okay, actually, you know what? Actually perfect. Absolutely perfect, because I just made a mistake. If you ever want to, if you've got an equation like this and you want to find out what t is equal to, swap the two numbers here. Swap t with s. So I've written this wrong. It should be t equals d over s. You can tell that it's the end of the half term. And I just have to swap them, and then that's done. In my head, I was doing something there. I said that 3 is equal to 6 divided by 2. So the rules of maths mean that if this is right, 3 is equal to 6 divided by 2. And if I keep my numbers as what they are, so 3 is 3 for S, and D is 6, and T is 2. Is 2 equal to 3 divided by 6, or is 2 equal to 6 divided by 3? Well, this is the correct answer. So T is equal to D divided by S. That's a nice way to check to see if you've got the answers right. When you're doing a triangle and you've got two things that are multiplied together, so for example v is equal to f times lambda, if they're multiplied together, imagine that there are two people who are forming the base of a triangle. So here are my two people. I just got to bear with me on this one. All will be clear. There's f and there's lambda as people. They are the base of the triangle for the other thing to stand up on. So if v is equal to f times lambda, they'll be the bottom, they'll be the base of the triangle, and v will go to the top of the triangle. It's okay if you want to use triangles. I prefer if you didn't, but if you decide that you're going to use triangles, you crack on. But you write down your equation. Here are some units. Meter, m, speed, meters per second, velocity, meters per second, velocity, acceleration, meters per second squared, time in seconds, force in newtons, energy in joules, mass in kilograms, frequency in hertz, wavelength in meter, work done in joules, energy transferred in joules, and power in watts. These are the most common terms that pop up in your exam. They might not say that there was a power of 6 watts and an energy transferred of 2 joules. What was the time taken? They may just give you some numbers and expect you to be able to identify that capital W means power, watts, and the capital J means joules for energy. And if you're asked for significant figures, then mark the first 3 numbers. So 456.1.23699. If it's asking you for 3 significant figures, then mark the first 3 numbers. So that's the first significant, second, and third significant figure, and then round the third number. So I'm going to get this rounded up here. The one next to it is 1, so I'm going to keep that as 6, 456 to 3 significant figures. Now, not going to lie, it is the afternoon of the half term. It has been a long half term. That was the fastest I think I've ever spoken. Thank you for listening. Remember that was just quick to help explain all the facts. There is more detailed lessons that are much slower on the YouTube channel. Go on to WHA Science and go to the bottom of the home page, or in fact any page, to get the link to my YouTube channel. Cheerio, goodbye. Please do some revision. Don't overthink about it. And if you've listened to this video all the way through, the password for my eternal gratitude and respect is purple chicken. Bye-bye. Say purple chicken, and you get major kudos from me. Adios.